Our next speaker is from Spain, Mr. Moises Oñoro from the University of Carlos III in Madrid. They will be speaking about development and characterization of advanced nuclear materials because that is their PhD topic.
So, good morning, everyone. My name is Moises Oñoro from Universidad Carlos III in Madrid. First of all, I would like to thank FuseNet to give me the opportunity today to share with you this work, which will be part of my PhD thesis. And as you will see, everything is about temperature. From the hottest to the coldest temperatures achieved, we all have in mind the high temperatures that will be necessary to achieve our goals. On the opposite side, and just centimeters away from each other, we will develop the lowest temperatures needed to be able to confine our human-made stars. It could be necessary the highest technology developed so far. Our goal, and my goal, is to push forward to find the best materials ever made. This will shape every fusion reactor. But not only that, this will be of advantage of every kind of research field, industrial application, and of global social benefit. To allow operation at much higher temperatures than today's, advanced reactor concepts are being developed. Within Generation 4 concept for fission reactors, nuclear fusion reactors lays at the highest standards with unprecedented combination of temperature, radiation dose, stress, and coolant compatibilities. Thermal creep at higher temperatures and radiation dose and radiation embrittlement at lowers will limit structural material application. ODS steels and tungsten alloys are desired as structural plasma-facing materials at the moment. Eurofer 97 as reduced activation ferritic martesic steel is the structural candidate for ITER. First wall components are currently being developed. Building blockade concepts for ITER are based on an armor coated with a tungsten layer joined to a steel structural component. ODS ferritic steel is currently being investigated as an improved structural material candidate. In addition, the divertor will exhaust the major part of the plasma thermal power, sustaining the highest temperatures values. Thus, the development of joining technologies for the ODS steel supporting structure with the tungsten armor is an essential issue for its construction. Today, I will be presenting the most important results of our investigation about the characterization and thermal stability of an ODS ferritic steel. It was obtained via powder metallurgy process from prealloy powders and nanosized yttria powder, from which we will obtain the nanoparticle dispersion. Heat processes were performed for the powder consolidation, obtaining the first pieces of the material. Then an HCR process was performed on the consolidated materials for its microstructural development, obtaining about around a 70% of thickness reduction. With an annealing study, we selected 1273 Kelvin as the optimal annealing temperature. From this point, two independent thermal treatments were applied to the ODS steel. On one hand, a thermal cycling treatment, and on the other, a long-term aging thermal treatment. We obtained the first results on Vickers microharness focused on the annealing treatment. The ODS steel experimented a slight and stable hardening along the different annealing temperatures, but not at the highest temperature. This could be associated to mechanisms of microstructure recovery and recrystallization. Tensile test experiments performed at room temperature and 973 Kelvin are represented as function of the annealing treatments. This allowed us to highlight the 1273 Kelvin as the optimal annealing treatment. These samples were named as ODSR and used as reference for comparison. Now, from the ODSR sample result, we completed the Vickers microharness investigation. We observed a harness increase for both the cycle and the aged samples, named as ODSC and ODSA respectively. This increase was more evident for the aged material. We also completed the tensile test characterization. When comparing ODSC and ODSA with the annealing results, the bar diagrams, the strength parameters showed an improvement at high temperatures, while aging ODSA produced a general loss of the elongation values. Scanning electron microscopy revealed a stable matrix of submicron elongated grains following the HCR direction. Furthermore, two different secondary phases were identified along the three different samples, a tungsten chromium-rich precipitate in orange and a titanium-rich one in green. A semi-quantitative analysis of the chemical composition showed on the aged samples a reduction of chromium together with a tungsten increment on tungsten chromium-rich precipitates. This could be a hint of Levy's phase formation. Moreover, this analysis emphasized the stable composition of titanium on titanium-rich precipitates. From the morphological point of view, we analyzed secondary phases individually. They were fitted as ellipses, and we estimated the maximum to minimum diameter ratio. The round-shaped nature of titanium-rich precipitates prevails after the three different thermal treatments. On the other hand, tungsten chromium-rich precipitate started with a round-shaped nature after annealing, broadening for both cycling and aging treatments. Furthermore, the aging treatment promoted their diffusion along green boundaries that could be related with the loss of total elongation reported on tensile test. Finally, we are currently focused on sharp impact tests and surface fractographic analysis. We obtained the first results for the annealed and aged samples that will lead us to report the ductile to brittle transition temperatures and the involved fracture mechanisms. To conclude, I point out the most important results of our research so far, based on the characterization of an ODS ferritic steel and its thermal stability after annealing, cycling, and long-term aging thermal treatments. Thank you for your attention, and I will be happy of answering any questions.
Thank you very much, Moises. A great talk indeed.